Okay. Nice. Beautiful. All right, so let's get started here with 63. Now 63 would be on this second page that I said I had to print up here. All right. Oh, yeah, this is a nice design for, especially for any of you guys going into electrical engineering. You got to constantly think about this. It says to prevent damage from arcing an electrical motor. So I'll just kind of tie it together with this chapter. That I wonder why I ended up putting it on slow-mo setting. Here we go. So what was I saying here? So an electric motor has all these windings in it. We talked about that a couple chapters back, where you have something like a magnetic field, and then the current goes through the coils, and that puts a force on those wires. And if you put equal and opposite forces, but on two tops of the wires, it twists it, it makes a torque. So the whole design of an electric motor does have these looped wires, which also means it makes some inductance. And here's what that means. That means, of course, starting up the motor, it takes a while for the current to build up, but it also means turning it off, it takes a while for it to go down. And if you try to disconnect it, so if you just have a simple switch, and this is showing it well, that if you have this 12-volt switch and you turn it off and the current flows, let me forget this resistor for a moment, and it goes through this motor, then you go to turn it off and you open this switch, you're trying to shut the current off very, very, very quickly. Now, remember, the EMF in an inductor is minus L di dt. So in the process of trying to open the switch, and meaning changing the current by an enormous amount, you produce a high voltage. And so what ends up happening, if you don't have this resistor, is that you open this switch, there's such a EMF created here that it makes, thousands and thousands of volts. And that thousands of volts do all kinds of possible problematic things. We got to remember all these wires are insulated, and they're next to each other. And the insulation is only good for a certain amount of voltage. If this is a wall plug, we usually make it thick enough so that you can handle the 120 volts, at least in North America, and probably the rest of the world would be about 240 volts. But if you unplug this quickly or turn it off quickly with just a single pole, single throw switch, you could end up producing so much voltage that there is actually a breakdown of the insulation and current flows, and you damage the wires that are next to each other. And most likely they're the wires in the motor, and you damage the whole motor. So you don't want a process where you turn off the motor and you destroy the motor. That's something you need to avoid. Another option is that maybe if you don't damage the motor, maybe there's so much voltage here in the switch that you got to remember when you first open the switch, the distance between the wires is microscopic. And so what you can do is get arcing inside that switch. And that, of course, that switch with arcs could be dangerous for people touching it. It could start fires. If nothing else, it just fries the metal connections. And you do that, 100 times, and the switch doesn't work anymore. So again, nobody wants an electric motor like a vacuum cleaner that's going to stop working after 100 turnoffs. So to answer that, you put a resistor in parallel with that. And that's what this problem is going to do. And what you're going to see here is then we can control how much back EMF there is created by the size of this resistor. And so we can control it and keep it below a certain level. So that's the engineering design. Of course, the bad thing about that is when you have it then closed, some of your electricity is flowing through this resistor and not going to your motor. So you might say you are consuming more electricity than is being needed to run that vacuum. So that's the bad side of it. But like I said, the good side is at least now we have an electric motor that we can turn off thousands of times, if not tens of thousands of times, if not hundreds of thousands of times, and it still work. And that's depending on the size of this resistor, is probably worth the consequence. So we're going to put a reasonably high resistor, but yet low enough so that the reasonable high makes that our drain current while we're operating the motor is not so great, so we're not wasting too much, but also then when we turn it off, it can drain through there and not have such amount of back EMF that we damage our electronics. So very, very common design, and I picked that problem just for it. I did such a practical and important design for anybody going into electrical and engineering. It's just one of the standard tricks that an electrical engineer would need to know here. All right, but let me actually do the problem here. So to prevent damage from arcing, so that's part I'm saying about arcing, but there are other reasons it can be damaged from arcing in an electric motor. A discharge resistor, that's this one, is sometimes placed in parallel with the armature. So here's the armature and here's the parallel resistor. If the motor is suddenly unplugged or suddenly switched off with a simple switch, we could also avoid this with a more complicated switch, but there's nothing you can do if it's unplugged. So you've got to have this for the case of when it's unplugged. If the motor is suddenly unplugged while running, this resistor will limit the voltage that appears across the armature and therefore saving damage to the motor. Consider this. Consider a 12-volt DC motor and an armature that has a resistance of 750 ohms and an inductance of 450 microhenries. Assume that the magnitude of the self-induced EMF in the armature coils is 10 volts when the motor is running. Now, this is an interesting added piece that may not be obvious, but when you have this coil of wire with current flowing, now remember it's in a magnetic field. That's what made the motor. And so again, we talked about that a couple chapters ago, but what we didn't talk about, and so what would be new in, I guess, this chapter, but this chapter is an application of last chapter. So these last two chapters is that this spinning coil gets a change in flux and produces a back EMF. So the reason why the current is having a hard time going through the motor is not just because of the long length of wire all twisted around, which you might make thin. So in other words, it has resistance. It's actually more interesting and more complicated is there is a back EMF while the motor is spinning, because while the motor is spinning, it makes an EMF because of the change in flux by the way the motor is designed. So the good thing is when you put current through a wire or a loop of wire in a magnetic field that spins, the bad part is it spins, it makes a back EMF. So they're not really getting into that too much detail. We're going to do more of that next chapter and not too much more. That's just as far as we're going to be able to get, and the semester is going to come to an end. But those of you going into electrical engineering later on would spend a lot more time analyzing this. But you get a back EMF. In fact, in this case, it's 10 volts. So I would say what's opposing the current from coming is not just resistance, but also a back EMF. In the next chapter, we'll call that a reactance. And so you have resistance as well as a reactance from keeping the current from flowing. Okay, so with those two effects in mind, although they've made it easy for us on this chapter because we really haven't done reactance, that's coming up next chapter. They say just treat all that as a total of 10 volts. Okay, so we will here. So it says consider a 12-volt DC motor with an armature that has 7.5 ohms of resistance and an inductance of 750 ohms. Assume that the magnitude, there it is, of the self EMF in the armature is 10 volts when the motor is running at its normal speed. The equivalent circuit of the armature is shown in this figure. Okay, so here it says, calculate the maximum resistance R. Like I said, we want the R to be big so that we don't have too much drainage current, but also we want it small enough that we don't get too much voltage. So the maximum resistant R that limits the voltage across the armature to 80 volts. So we build our motor with enough grit, if you will, so it can handle up to 80 volts when the motor is unplugged. All right. So we're going to put in the appropriate resistor that will allow it to never exceed 80 volts when it's just quickly unplugged or switch quickly turned off. All right. So maybe to start this, I'm going to do this. I'm going to do a loop. I'm going to do the outer loop. So with the switch closed and just looking at the armature, I'll add the shunt resistor or the drain resistor here in a second. So 7.5 ohms. Then here's this inductance, 450 millihenries, and 10 okay, maybe I better put 12 volts over here. All right, so what they're trying to say here is if you've plugged in this motor and you've got it running for a while, so again, for lack of better, I'll just say, what if this is a vacuum cleaner motor? So I've turned it on, I'm running it, I've been vacuuming the living room, so it's been on for 5 minutes. We've reached steady state. Now, the reason that's important is because the EMF is minus L di dt. And as we saw in many examples here today, with DC circuits, and I'll say it again, that's going to change in the next chapter, but with DC circuits, there will be a point in time where things settle down and there's no more change in current, which means there's no voltage on the inductor due to the Faraday's law. So I think they're saying here, take it as that situation. And again, maybe my vacuum cleaner is a poor example because most vacuum cleaners for your living room, you plug into the wall, that's not DC. So maybe I had to look at maybe one of those car hand ones, or the ones for the car that you plug into the cigarette lighters or utility plugs. They're 12 volts. That'd actually be good because it is 12 volts and it would be DC. So maybe I should do that. So I got this, let's say, pretend I got this little handheld vacuum cleaner that I can plug into the either the cigarette lighter or utility plug in my car, and I'm running it. And so I've been running it for 5 minutes. And so what I'm getting at is when it comes to adding up the voltages around the loop, starting down here, I would go 12, then I would go minus 7.5 I for whatever current is flowing through here. Okay. Now, you may argue that, well, there's a short circuit resistor. Okay, so technically the I in the battery is a little bit more than this I. So this I is actually over here. And maybe to distinguish that, I'll call this over here I naught, and it splits off. Some of it goes down this drain. Maybe I'll call it I sub D for drain. But just the regular I is the stuff I'm worried about. If I do this loop, it goes through the armature. This is where the inductor comes in. And so I would say minus 0 there. There is no more change in current after a long period of time. Then minus 10 equals 0. And you see that alone can get me to solve for the current I. So I can get this current, even though I don't really know what the current is in the battery, because it would be a little bit more because it would include the drain. Although, again, I can do the drain one. But let me just start here with how much current is in this motor. So if I put the 12 together with the 10, I get a 2. And if I move this 7.5 to the other side, it becomes a positive. And so I get a 2 divided by 7.5, and I get 0.267 amps for the amount of current that is in the motor, the armature of the motor, after it's been going for a significant period of time. Okay, well, why do I care about that? Well, here's the big thing. Here's the lesson that if you didn't catch it, let me emphasize. Inductors have this nice property right here where we can say a couple things about them. One, and we said this a lot today, but the other two we haven't. So we need to spend some time talking about the other two. But this equation has some interesting consequences. The first one I just mentioned and have mentioned it on a few other problems today. And that is that after a long period of time with DC circuits, the di dt would, or the current would not change. So di dt would be zero, the voltage would be zero, and that's what this term would represent. And we don't even need to think about the inductor. And so we can think of the inductor as a wire. And that's after a long period of time. What I have not seen yet in the problems we've done today, but I know it's somewhere in these other problems, and it's certainly in the book, is what would you say about when it is first turned on? And for that matter, when it is unplugged, those kind of go into the same. So I guess I said there were three because of unplugged, but maybe this is one and the same. But right when there is an initial change, maybe that's the best way to say it. So one effect is after a long period of time, this is zero. The other effect was right when there is an initial change. Either you first turn it on, or you first unplug it, or you first plug it in, whatever. Right when you make that. You see, when something significant like that happens, and in this case, let's talk about turning on the motor the first time. Okay, so before we had running it for 5 minutes, I would have closed the switch, and at that point, the current would have been changing dramatically. In fact, the current would change so quickly that there would be enough voltage here that it would stop the current. Now, you would never get so much voltage that the current would flow the other way. So that's important to realize. But what is part of the argument here is you never change the current instantaneously. It's got a continuous, the function of the current is continuous. So in other words, if I were to plot the current as a function of time, before I turned it on, the current would be zero. After a long period of time, it would go up to this number. Its transition would be this exponential, but notice it's continuous. Now, I'm not saying it's continuously differentiable, although it would be there too. We kind of draw kind of a quick transition. But I am trying to say that, well, maybe I should draw it as not only a continuous function, but a continuously differentiable function. But we have to have both of those criteria. Otherwise, this number just goes to infinity and the energy is infinity, and you just physically can't have that. So the current then, we argue, does not change instantaneously. It's continuous. So if the current was zero the moment before I close the switch, the moment after it's still zero. And the only way you can get that is if there's some voltage in this inductor. And so that would tell you how much voltage there is right when you close the switch. Now, that's not part of this problem, so I won't go down that road. It's part of some other problems. But I will say this then. Let's do this problem where, first of all, we close the switch. Then we leave it on for a long period of time. So again, maybe we're vacuuming for 5 minutes. And now we can treat this as a wire, but now we're going to unplug it. And when we unplug it, the circuit looks like this. Here's the armature, 7.5 ohms. Here's the wires in the armature representing 450 milliamps. Here is the back EMF due to the spinning of the motor in the magnetic field, 10 volts. So this is our model of our motor. Or maybe I should have said the resistance isn't added. It's part of the fact that we've got wires that are real thin wrapped around enough to make this much inductance, okay? So these are not separate items. These are actually just the wires wrapped around in a magnetic field. So spinning magnetic field makes that. The wires coiled up makes that. And the fact that the wires are long and probably thin, so we can make a lot of coils, makes that. So that's just the building of the motor. Okay? But then once we unplug it, we have this circuit. Because over here, we're saying we opened the switch and presumably we want this resistor here to drain off the current so it doesn't, go back and arc here on the switch. So I'm going to just say, okay, that's kind of out of the picture now. We opened the switch. But here's my comment, is that there would be a changing of the current enough to produce enough voltage here in the armature so that the current does not change instantaneously. Now remember, before we open the switch, we just argued that there would be a current of 0.267 amps. So again, when the motor was on, that current was going like this, and a little bit was going through this drain. But here is where now you can see the purpose of this drain resistor, because when I quickly disconnect this, we are going to get that much current immediately after we unplug it. This is my statement that there would be enough voltage, however much that needs to be, to make sure that there is a big enough EMF in the inductor to make sure that the current does not change instantaneously. Again, if the current changes instantaneously, to stop current instantaneously takes an infinite amount of power. That's not possible. You cannot change current instantaneously when you're on an inductor. So here's what we know, and this is the key to solving this problem, is that this current will flow through this resistor and on around. Now, it will quickly be decaying away because, again, as you can see, for this inductor to even have a voltage, there has to be a change. So there is both a current and a change to it. And so it's quickly dying away. So in order to produce quite a bit of voltage, it's got to quickly decay away. So this current changes quickly. It would be something like this if you plotted the current as a function of time, calling 0 time when you unplug it. So you have a constant current, and then you unplug it. It's still at that moment going to be that same value, but it's going to decay away very quickly. The slope of this needs to be a big number so that we can produce enough voltage that would then make the current this much. And so here's how I'm going to solve a problem like that. But let me just kind of summarize, because like I said, we did like 3 problems, and this being one of them, where we said for an inductor, if you have an inductor on for a long period of time, you can treat it as a wire. You can treat it as no voltage because the di dt is 0. But same logic for an inductor. When you make a change, the current will begin to change at such a rate, either high or low, but enough to create enough voltage to keep the current constant, or I should say continuous. It'll quickly change. So a nanosecond later, it's going to be a lot less. But at that instant, when you open it, it's got to be the same. And I'm going to use that. Okay, I'm going to use that right here in this problem to then say that if I wanted to know the voltage across this drain resistor, which I will point out is the same as across the motor. So I'm trying to protect my motor and keep this voltage below something. I have V equals to IR. And so if I want V to be less than some value, it's got to be less than some value because I don't want it to exceed some value because, like I said, all these wires have insulation on them, and I will run into troubles if they exceed a certain value, depending on what I designed for and how big I made the insulation. So in this problem, it says calculate the value of R that limits the voltage across the armature to 80 volts. So we want this voltage to be less than or equal to 80 volts. Now the voltage equals to IR, and that means we want R to be less than 80 divided by current. Now, the current then would be changing, but of course at that moment that you close the switch, or excuse me, you unplug it, the current is at its maximum, 267, and then it decays away. So the smallest resistance would be calculated when the current is at its maximum. Well, later on, this number would get smaller, and the resistance that we would need could be bigger than that. But that's the idea here, is what is this resistance? So this resistor needs to be less than, maybe I'll say equal, so we can actually equal 80, less than equal, less than equal, less than equal. And so I'll take my 80 and divide it by that last answer, which is the current, and get 300 volts. So we're saying if we put a drain resistor right here of 300 ohms, and after we've had this on for 5 minutes or probably a lot less, and then I unplug it, it's like, like I said, if this was a little handheld vacuum for my car, as soon as I plug it out and pull it out of that cigarette lighter there, the current's going to race through here, and I'm going to get a voltage way above 12 volts. But if I set this at 300, I will only get 80 volts. Now, look what would happen if I set it higher at, say, 500. Then I would have 500 times 0.267, and I'd get a voltage of 133. So that's what I'm saying here is we better not go too high on that resistance. And in fact, you can see now that the lower the resistance, the lower the voltage is on the motor. So in one sense, I want a low voltage to protect the motor when I unplug it. But on the other hand, remember, we're draining here. So we don't want this too low. Otherwise, it's just wasting electricity while it's plugged in. So at 300, I would go 12 divided by 300. And the draining current, which back in my circuit over here, I called it I sub D. So I sub D at this value is 0.04 amps. So I'm wasting 0.04 amps during the whole time I've got my electric motor on. But I would argue that that's a small enough number that it is so worth it that it protects my motor from up to 300 volts, because that's what I will get if I accidentally unplug it or purposely. I'll get 300 volts inside. And then, of course, we could play with the numbers here and say, okay, well, maybe I don't want to put so much protection in my motor, so maybe I only want to protect to 200. Okay, so then I got to have a lower resistor here, which I get more drainage. So at some point, it's a trade-off between how much drainage do I want while it's plugged in versus how much protection do I want when I unplug it. And so my design criteria would be hopefully a nice balance between all those. Well, so with that said, maybe I should check the solution guide here, because this one wasn't a hard calculation, but it conceptually was very interesting. Yeah, so they said R has to be less than or equal to 300. 300 would get you exactly 80. Less than 300 would get you under 80. So that would actually extra protect the motor. But like I said, it's a bad thing because you get more drainage. So you decide on the criteria. Nice. All right. Hey, we did it again. We got through your whole list today. Maybe I'll come back here to the chat. I see James jump back in here and thank you. 3, 4, 9, 10. Are those more on the list? Is that what I'm hearing? I'm gonna try number 3. All righty. What time is it? 3:46. Nice. Do number 3. Unless you got something to add, James, here, or are you just kind of?
That's okay. I'm content to just lurk in the background.
Okay. Yeah, I totally understand that. I usually am too. And most people are. So I think that's why most people just kind of wait for the videos to come out. They probably appreciate you guys throwing all the questions out there. Hey, just ask a bunch of them. Ask anything. Keep them busy. Get them all recorded. All right. And hopefully, I don't think people do, but there could be one or two just cheat themselves is what happens, and they just copy it down without understanding. So, but most of you do this, with good intent, knowing that, hey, this is not only good stuff, fun stuff, but it's my career connected stuff. So I gotta know this. And then maybe not so much for you CS guys, but definitely for any in electrical engineering. In fact, I don't think I've got a chance to say it recently. I'm going to say this semester, maybe I did, but I always like to say to people who, a lot of people come in thinking they want to be mechanical engineers, and there's nothing wrong with that. But I think a big reason they say that is their life experience up to this point has been far more mechanical than electrical. So I always like to say, I did say this to a few people a couple of times. Okay, good. But usually when sitting in lab, I talk to people and say, and that's fine, but just keep an open mind this semester because we're going to do some neat electromagnetic stuff. And for some of you, this will be new. And for some of you, you'll just love it. And you'll just think, whoa, I think I want to change to electrical engineering. And this is your chance. I mean, this is your gateway, if you will, to say, hey, I've been exposed to things I hadn't before, and these are better than mechanical. Of course, others of you will look at this and go, oh, no. I like mechanical things, and it's just confirmed it. And that's good too. So that's part of the learning process. But since this is the fundamental, both mechanical and electrical, all of you guys need to take mechanical and electrical moving forward. Okay, so it looks like number 3 would probably be back on that first page. So let me find my computer here and go back to the first page and move this second page out of the way. So number 3 says that a 10 millihenry inductor carries a current, and they give us a sinusoidal. Okay. What is the self-induced EMF as a function of time? All right. So this one is a little more plug and chug, but it's also one that where the current changes with time. And like I said, it never stops changing with time. So this really isn't a DC circuit. And I was saying most of our problems in this chapter are DC circuits, and we get to the AC in the next chapter. But this really is kind of an AC, but it's not a real complicated one. I think that's why they did it. And you're going to see a lot more of this next week when we get into chapter 33 here. But to figure out what the EMF is, then I just put in my value with a minus, and the inductance is 10 millihenries. And maybe I'll comment that a Henry is, again, 1 volt when you are changing the current by 1 amp per second. So there's my 10 millihenries. And if I go ahead and take the derivative of the current, I'll write out the equation up here. The current is defined in this problem to be the maximum current times the sine of omega t, so some angular frequency, as we talked about before. So the maximum, I'll just leave alone here when I take this derivative. And the derivative of a sine, is it negative cosine or just cosine? It'd be one. Yeah, so it's just cosine. Omega t with a chain rule, which is the omega. So this would be negative, and if you let me put this in a decimal, 0.01. 10, yeah, so -2. Maximum currents, they go as 5 amps. Angular frequency, now you'll see here that they said 60 hertz. They did this for the frequency, which is the omega over 2 pi. That's kind of a discussion we had earlier in one of the problems. That, don't confuse the frequency with the angular frequency. And so they say that's 60. So this omega is 2 pi 60, which, by the way, that 60 is going to be an important number for us in North America because that is the wall plug. So our whole electrical grid is designed with a spinning generator that goes 60 times a second. So the angular frequency is 2 pi times 60, which is 377. And so that's our angular frequency for North America, whereas the rest of the world tends to be around the 50. So, and again, each of those have their own pluses and minuses. Okay, so there is the maximum current. There's the angular frequency. And I don't know if I can put anything in here other than maybe put 2 pi times 60t, which simplifies to 120 pi t. Because they say, and I hope they said as a function of time. Yeah, they're not having me put in a value of time. Now, before I do the numbers, I guess I also want to check my units. Remember, this first number was a volt over amp per second. That's a Henry from this one. This is the maximum current, so that's an amp. And this is the frequency, so this is a hertz, so it's per second. So it would be over a second. So that amp would cancel with that amp. That second down in the denominator of the denominator would cancel with that second in the denominator. And you would be left with just volts, which we should be, because this is saying what is the EMF under this scenario. And an EMF is a back voltage, or it's just a voltage. Usually when we talk about back EMF, we're talking about the voltage created because of a changing magnetic flux. Well, whether the voltage comes from a changing magnetic flux, a changing magnetic field, a changing current, or just charges, like we did for batteries and capacitors, then it's, again, just a voltage. All right, so negative, and putting in my numbers, 0.01 times 5 times 2 times pi times 60, and it looks like a back EMF of about 18.8 volts. And maybe this will be a good time to say, this back EMF would be what you would be getting if there had, back to the other problem, 63, the spinning coils in the armature of this motor. And of course, whether it's a sine or a cosine depends on when you kind of start your clock, because we know that a cosine function starts at its maximum and goes back and forth. But we also have the freedom to talk about the time. So we can put time equal to 0 anywhere we want. In fact, a negative cosine would start down at the bottom and go like this. So I would also say that calling this a positive or a negative would be fine, as well as calling it a sine or a cosine. But you could even do something in between. You could call it a sine omega t with some phase. Just a matter of where you decide to kind of put your vertical axis. and say, okay, where do I want to call time equals 0? Because if you do it here, you can see that you probably call it a negative cosine. If you did it here, you probably call it a positive cosine. And if you did it here, you probably call it a plus sign. If you did it here, you probably call it a negative sign. So I'm going to look at the answers, but I'm not really going to care if they go plus or minus or if they go sine or cosine. But given that they gave me it as a sine, I have a feeling that they'll have a cosine with the negative. That would be the most likely, and that's why I kind of was following that strict arithmetic. But that's always an important skill, is the arithmetic. And how does it relate to the real world? So what things can we kind of just ignore in our arithmetic, like a sine becoming a cosine or a plus becoming a minus? But they have the minus, they have the 18.8, and they have the cosine. And then they multiplied this 120 pi out and got 377. So, yep. Next. That one looks like a good match and a good one to do. All right. So let me come back to your question. The other one was number 4. Okay. Number 4. 357. Okay. Number 4. All right, so number 4 should be on this first page on my computer here. All right, so it says an EMF of 24 milliohms is induced in a 500 turn coil at the instant the current is 4 amps, but is changing at a rate of 10 amps per second. Okay, so just kind of make it clear. If here's current, here's time. At some moment in time, I don't really say when this is, I'll just put T naught. There is a current of 4, so I'll put a 4 on that axis, but it's got a slope of 10. So maybe the function of the current looks like this. Who knows? But it has a value 4 amps, and it's changing, has a slope of 10, and that would be amps per second. Then it says, what is the magnetic flux through each turn? Oh, good. And I can see why this is kind of early in the homework problem number 4, because this gives me a chance to say that the fundamental physics is Faraday's law. And that's last chapter. Faraday's law says that there'll be an EMF. And so if it's in a circuit, we call it a back EMF. All right. But there'll be an EMF. And actually, if it's in the circuit itself, and so it's having an effect on its own circuit, not an adjacent circuit, then we call it a self-back EMF. And so sometimes we have circuits next to each other, and one circuit affects the other. So we call them mutual. And we don't point calling it back, since mutual doesn't really have a forward or back direction, but it's a mutual EMF. Sometimes also called a mutual back. So a little beyond the scope of this class, as I said in the earlier one, this is not a circuits class, so we're not going to analyze everything involving circuits, but our big picture is really Faraday's law, and then an application of Faraday's law. And there are many we already saw in chapter 31. But a really big and important one that we give a whole chapter to is within a circuit itself. And so we say that the reason there's a change in flux in a circuit comes back to the fact that the currents would be changing. And so all the other factors that have to do with flux, remember, flux has to do with the strength of the magnetic field, which does come from the current. That's why the current is there. But also the area. So a lot of things involving the area get absorbed into this constant called the inductance. Okay. So again, looking at physics, I would focus on this equation. Looking at how the physics was applied to a circuit, so being an electrical engineer, and looking at just a single circuit on itself without a spinning motor too, I might add, because here we're saying the change comes only from the current change, not from the area changing, not from the angle changing. Those are other reasons why. That's why the physics is probably more important than this equation. This is kind of a special but important case, an applicational case. All right, but what I'm trying to point out is these are the same. And with that in mind, we can do two steps. The first step is we can cancel off the negative on each side. And the next step is we can integrate both sides. Because when you integrate both sides with respect to time, the right-hand side just becomes L times I. The left-hand side becomes the number of turns in this coil or solenoid or whatever it is, toroid, coaxial cable. But once we integrate this, we get the flux. And the whole reason we have an N is this is the flux through one turn. Okay. And that's how I want to solve this. And so this one is connecting the physics in chapter 31 with this chapter, and it's even asking for what is the flux. So it's asking for this side of the equation, but it's giving stuff on this side of the equation. So the flux would be the inductance times the current over the number of turns. So this one said that the L, okay, yeah, this will be fun. They did not directly give me the L. So more to talk about on that. So I'll just leave that as an L. They did give me the current. Current is 4 amps, okay? And they gave me the number of turns, 500. Okay. So let me call this equation 1 and keep that handy. But the other piece of this is they gave me the voltage and they gave me the rate at which the current is changing. So that sounds like this equation here. Let me write it again. EMF equals minus L di dt. And without worrying about which direction, so the magnitude of voltage, I won't worry about that minus sign. But they tell me how much voltage I'm getting. They don't give me a circuit or tell me which direction. So not worrying about the plus or minus, this voltage is 24 millivolts. And the current is changing at 10 amps per second. So this is what I meant by saying they didn't directly give me the L. I didn't notice that till I got to this point. But I can get that L, and I guess I can do that by moving the 10 over here, and I'll put it under the 24. So that'll become 2.4 times 10 to the minus 3. So that's the inductance. And so now if I put that here, I'll get 2.4 times 10 to the minus 3 for the inductance, and a current of 4 and 500 turns. And I'll do the number, but let me also look at the units here. Remember, this first one is the henries. And so these are actually millihenries, but they're henries. Remember, a henry is 1 volt per amp each second. And I feel like I kind of need to focus a little more on that one because the henries is a weird unit and very new to probably almost everyone here. So that's how many henries there are. Of course, then multiplied by the number of amps here. Okay. And so if I cross this off, I get a unit of a volt times a second. Now, putting my numbers in here, and still working with my units here, well, this would be 2.4 times 10 to the negative 3. times a 4 and divided by 500. So we're looking at 1.29 times 10 to the minus 5. And that's supposed to equal the flux. And I'm not saying I'm even wrong yet. It's just that when we were introduced to flux, either electric or magnetic, but we've been dealing with magnetic lately, we said this. We said the magnetic flux is the integral of B dot dA, which means we're taking the strength of a field. And so unit-wise, it would be Tesla times a meter squared. We actually call that a Weber. And that's a unit we haven't used today. And it's not a very common one, but I think your book mentions a Weber. But so whether we're going to call it a Weber or a Tesla times a square meter, either way, this at first does not look like that. Let me keep working with it. So let's go on here to page 2, because the units I have is a volt times a second. Okay. So maybe it's worth going all the way back to our first chapter on magnetism, 29, and say, okay, now what really is a Tesla again? See, a Tesla was a force of 1 Newton when you had 1 coulomb of charge moving at 1 meter per second. Okay, so keep that in mind, because I'm going to play this little trick, if you will. A volt, remember, is a joule per coulomb. Okay. So looking at that, and of course, looking what I have here, let me do a little bit of adjustment. I'll leave the Newton in the top and move the second up. And I will leave the coulomb and the meter in the bottom. Okay. Let me go ahead and then multiply top and bottom by a meter. So I get a meter in the top and another meter in the bottom. Okay. And let me point out that a Newton times a meter is a joule. So maybe I'll just replace that with a joule. Okay. So what I'm hoping you see is these two is a joule, and that's a joule times a second, and that's a coulomb. Let me group those together. Joule, second over coulomb, and then I'll move the meter squared to the other side with the Tesla. So this joule times a second over a coulomb actually is the same thing as a Tesla times a square meter, which is that Weber that I was commenting about. That is the unit that you're probably very familiar with in terms of what is the flux. So electrical engineers love to talk about flux in volt times seconds because they're usually interested in the flux of how it produces then a voltage. And so they like the unit of voltage hanging around. But as physics people, we really like the units of flux in the Webers because they're going back to the mathematical meaning of what flux is. It is a field through a square or through some area. And so it's a field and an area. And it fits the definition of what we mean by flux. All right, so I can just say that all of this, a volt times a second, is a Weber. But this one was probably the hardest one we've done so far. So it was, I thought, worth our time to go through and talk about the units and say that that's probably what I'm going to look up is a volt per second, but knowing that that's a Weber, I'm not going to be too bothered by it. So when I look at number 4, it says 19.2 micro. Oh, and they do Tesla times square meter. So they did convert the units. They didn't leave it like an electrical engineer might. They did then do the engineering units. They made this bigger to a 19 and this times 10 to the minus 6. So 19.2 micro Webers. Next. And I think that was it. I don't think there was a part A or B, right? What is the magnetic flux? Yeah. Okay. Yeah. All righty. Well, I'll keep working through this list here. Let's see. Oh, I got to go. That one's on the Zoom here. All right. So after 4, how about number 9? Write down the time. All right. Let's try number 9 together. So let's see. Number 9. So number 9 says a self-induced EMF in a solenoid, we know its shape, of inductance L changes in time as given by this equation. EMF equals some initial value and then decays away exponentially. Okay. Find the total charge that passes through the solenoid, assuming that the charge is finite. Now, I'm not real sure why finite. Okay, I think there's going to be some limits in my math, and looking ahead, I would say that would kind of require K to be a positive number. K can't be a negative number. Otherwise, we get exponential growth, and the EMF just keeps getting bigger and bigger and bigger and bigger with time. Or if K equals 0, we would have just a constant EMF, and there would never be a total. It would just keep going on forever and ever. Now, if it is positive number, it decays away, which means eventually the current goes away. And so I think that would be finite. Although if it decays away, it never quite goes to 0. So there might be some other mathematical limits, but I don't foresee it. So I think our mathematical limit here is that K has to be greater than 0. Otherwise, we won't get a finite number. The integral won't be defined. It won't be a closure to it. So let's see what happens. And I say integral off the top of my head, so I should probably say what I'm thinking. See, it says total charge, and here's what I'm thinking. I'm thinking if I want to find charge Q, I add up a bunch of DQs. So that's kind of the logic that's going in my mind. How much charge goes through in this microsecond, and the next microsecond, and the next microsecond, and the next microsecond, and the next microsecond. So I'm going to add it up for all of time. So what I need to do in my first step is to switch from an integral of dq to a dt, right? I want to add up for all moments in time, and so my time can go from 0 to infinity. Now, of course, to do this switch, I would be multiplying top and bottom by dq. And then grouping this together means that I would have an integral of the current added up over time. And I probably could have started there because I think I learned enough back in chapter 29 that I know that current is the rate of charge at that moment. So if I add up all those moments in time, I would get the total charge. So you probably could have started here, but I think it's neat to see kind of the math evolve along with the integral kind of evolve in your thinking process. So now we can do Ohm's law, because the current would be I'm going to say V over R. The self-induced voltage of a solenoid of inductance L changes with time according to this. Find the total charge that passes through the solenoid. Now, I suppose also I just realized that maybe I'm not going down the right path because I was gonna do EMF divided by resistance. They don't really give me a resistance. So I'm looking at this saying, I think I'm gonna run. So let me put the pause on this. However, this is still true, and I'm thinking I'll still need it, but I'm not 100% sure. So I'm gonna put a little box around it. Because in my mind, I'm thinking of an inductor. There's other ways of getting the current besides Ohm's law, and I don't really have Ohm's law. So let me do this. That remember that the EMF is minus L di. See, and I'm looking at the problem, and they gave me the L, and they gave me the formula for the EMF. So I think that allowed me to get current. Yeah, and so that's my new approach, is to say, look, I need current, but it's not really going through a resistor. So this would be inappropriate. They don't even really say anything about it. It's going through an inductor. All right, so let's see where this gets me. So let me put in this equation where it says E naught e to the minus kt is the EMF. I've got minus L, and I got di dt. And this is looking like a great equation to solve for the current. It looks like a separable equation. The rule is try to put everything with current on one side and everything with time on the other. And the constants don't really matter where you put them. So the big thing is to make sure I leave the e to the minus kt with the dt that I'll bring over. The constants could stay where they are, although I prefer they be together so I don't have constants to worry about on both sides. So why don't I put them on the left-hand side and then say, all right, let's then, now that we separated it, integrate here. And do they say that the current only say it starts at 0? And it probably doesn't because it's decaying away. So maybe for the currents, I should do this and see where this leads me. Let's say we start with some initial currents at time 0. and then go for a period of time. We could put 1 second, 2 seconds, or 3 seconds, but let's use it as a variable. Let's say it goes to t seconds. Then it would go to a certain current. And that's what we'd want to solve for, that current. So the right-hand side of this equation would be current minus initial. I think we got to have a little talk about that. Over here, we will have the minus E naught L. And when I integrate this, I get e to the minus kt, and I think minus kt evaluated from 0 to t. Let me talk about that one in my head for a moment. If I take the derivative, I get the same thing, and then the chain will give me a minus k, so that's going to give me that. Okay, so that's the integral. The two minuses I'll take together, and then the constants I will put together. And then I would have e to the minus kt, and then minus e to the 0. And then that should equal to the current as a function of time, and then the initial. So, page 2. I'm kind of wishing maybe I did instead of a definite integral, I don't wish if I would have indefinite and had a constant, but whichever way is easier to see. But I like this because I got this E naught LK e to the minus KT, and then minus some constants, E naught LK. Then on this side, I've got the current as a function of time minus some initial constant, some value. So these two must be the same. I mean, this must be the initial current. And so the current as a function of time must be E naught LK, and then it decays away with a minus KT. So that's what I really needed and will need to solve this problem up here. So I'm going to come back to that in a second. But I want to check here. If I were to plot this, it looks like it's a decaying exponential. So it would start with this E naught L over K and decay away. And that means its initial current is E naught L over K, which agrees with our argument here, that those would be equal and cancel off. Okay, good. So maybe it wasn't so bad to do a definite interval instead of an indefinite. Because I knew this was going to throw me crazy because I don't really know what this starts at. I know time can start at 0 and then decay away, but this is much nicer when that's 0 or a known value like 20, decays away. All right, so with that in mind, let's go back to this equation we got started with that said, okay, what's the total charge going through this? It would be an integral from 0 to infinity of E naught LK e to the minus KT dt. And notice that was the part I was kind of saying earlier that we would run into trouble if K was either a 0 or a negative number. Definitely 0 down here. Okay. So as I do this integral, I get E naught L over K. And then when I do this integration, I get e to the minus KT over K. I kind of oh, like my A, I don't recall them saying anything about K. I don't know if I can put in a number. Right? Although, oh, well, okay. So maybe it just has to be symbols. Okay. I was kind of feeling better if it would have been upstairs. And I wonder if I made just a simple math error, but if I did, I don't see it. So let me keep going. Now that should be a minus. I should put that in there. Now let me just double check that. That'd be a constant. And when you take the derivative of that, okay, so we're going to integrate it from 0 to infinity. So E naught LK. And so let me put in infinity here. Actually, why don't I move that to a negative and a K squared? I'll move that out. So you have just the decaying exponential. And so this would be E to the negative infinity. This is where I have to be careful. It's negative infinity only if K is a positive. Otherwise, it's a positive infinity. It's not bound. And then minus E to the negative 0, if that means anything. E to the negative infinity, that's K's away to 0. And this is 1. Negative and that negative cancel off. So I get E naught LK squared as the symbols then for the total amount of charge. Let me check the answer here. 9. E naught, yeah, LK squared. So it's all symbolic. So I can't put any numbers in. They didn't give us any numbers. All right, nice. I think there was one more. I think we're also, and I won't try to do it in 2 minutes, so we'll go a little long here. But number 10, the next one. Okay. And number 10. Find number 10. All right. So number 10 says, show that I equals and I'm going to say that's probably initial, E to the minus T over tau, time constant, is a solution to this differential equation where I sub I is the current at time equals to 0. Okay, now here's the differential equation. And there is 2 ways we can show this is the solution. And I think they want us to do it the easy way, to be quite honest. Because solving this differential equation is not out of the question, but it's what they did in the book, and they got this, okay? And of course, I'll just comment on solving it. If I were actually solving it, I'd move this to the other side, minus L di dt, and then this would be IR. And then I would try my first approach, which can I separate the variables? That can I put everything with an I on the right and everything with a T on the left? And I can, because I can move this I over. I can leave the R here, and I can move the minus over and the L over, and then I could integrate. And actually, I'm almost done. I said I wasn't going to do it this way, but that's the way we solved it in the textbook and in the video lectures. Was, we didn't have anything to know what the solution was. We just actually solved it. Of course, if you did this, you would get from initial current to some current, and 0 time to t time would become minus RLT. And this would become then the natural log of I over I initial. Well, and then if I exponentiate it, it's e to the minus RTL equals I over I initial. And then you bring it over, you have I initial times E. And I'm going to write it just a little different. I'm going to put an L over an R because our definition of tau is L over R. So this becomes I initial e to the minus T over tau equals the current. So I guess that's the one way, but it's not the way I really wanted to show you. So I'll show you the second one. That wasn't bad. That's what we did in class. That's just directly solving the differential equation. But the way he phrases it here, the author, he says, show this as a solution. Usually what that means is take this and put it into the equation and see if it works. So let me take what he says is the solution and put it into that and see if it works. Okay, so really, I think he wants you to do this. So let's put in the current. So I initial e to the minus T over tau would go right there, and then times the R, then plus the L. Then we would put the derivative of that. So let me just take the derivative of that. The I initial, I would leave alone. Okay. Then I take a derivative of this exponential. Well, the derivative of exponential is pretty easy. It's just minus T over tau. In other words, the same exponential. But then the chain rule would give you a minus 1 over tau equals what? And the solution says it's supposed to equal 0. So that's what we're trying to see. Does this actually come out to be 0? Well, maybe the first thing I'll notice is that there is an exponential in each term, which can be first factored out and then divided. So that goes away. Same thing about a initial current. It can be factored out and divided. So that would go away. So on this first term, we're left with an R. The next term, I'll take that negative sign and put it here. And so this is an L. Now, this is a minus, which I already took care of, and then the tau would come upstairs. So there's the tau. And the question, does that equal to 0? And minus the L, and remember the tau is our L over R. Did I hang on here? Sorry. Back here when I took the derivative, I'll be trying to do too fast because they're into the day. I took it like I was integrating, so I put it downstairs. This right here should have been chain rule. And it would be in the numerator. That would make more sense. Okay, so let me put that in the numerator. So this actually then would be an R, and then it would be minus a 1 over tau times L. And what does that equal? And so the tau, remember, is an L over an R, which then makes the L's cancel and R, and sure enough, it does work. So it does come out to be 0. That mathematical form, when put into that equation, so that is a solution to this equation, it does come out to be. So that's really what they wanted to actually put the solution back into the equation to prove, or I should say the proposed solution. Put the proposed solution back. All right, well, let me come back over to the Zoom and see how you guys are doing. All right. Maybe it's time to call it a wrap now that it's 6 minutes after and say, hey, We got lots done today. I'm going to count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we did 12 out of the homework. So hopefully those were not doubled up from the other ones I sent out, some of the solutions. So, all right. Thank you very much. Yes, you are welcome. And like always, if there's any more you want me to do, send me them. I can make videos of them real easy. Never sure which is better, to have a video done during Zoom or a video, kind of a standalone one, put it on my webpage. Did you see the pictures? Oh, no, I didn't. I know the last one. Let me go look at those. I'll send you an email back. You did when we took the break, I was doing other things, like besides getting something to eat and stretching my legs and something to drink, but I didn't bother to look at my email. In fact, I'm looking at my corner of my box here, and it says I've got 58 new emails. So I guess it's time for me to start looking at my emails here. It's been zooming all day, so I haven't been really focusing on emails. So I will, and see what your pictures have to say. Have a good one. You're welcome again.